With topics like global warming always in the news, it's important for us to understand the properties of the gases that make up our atmosphere. In this year's lecture, University of Cambridge teaching fellow Dr. Pete Wothers shows us how each of the gases that make up the air around us has a vital role to play in our daily lives. I hope you enjoy the lecture. It's a gas.
Okay. Thank you very much. So in the lecture then, we're going to be looking at the properties of the different gases in the atmosphere. And I should just mention my lab coat here, which has been specially made for me. Well, this shows the proportions of the different gases in the atmosphere. So the yellow colour, this is the most common gas, nitrogen. The blue colour represents the amount of oxygen that we have in the air. The red pocket here shows the amount of the next gas, argon. Okay, and the little button just here shows the amount of carbon dioxide. Now we're going to be looking at the properties of all of these gases and see how important they are for us. But first of all, we're going to start off with the air itself. Now this is something that is all around us, but we forget about it, we don't notice it. Okay, I want to show you how important this is and that it really is there. Now first of all, I'm going to take all of the air out of this flask here. So at the moment, it's full of air. I'm going to use this special pump here to take the air out. So there we are, evacuating, taking the air out of the flask. And we're going to, well, we'll weigh the flask first of all. So we'll just set this to 0 on the scales here. So 0.00 grams. Now I'm going to open the tap, and we'll see how much the air weighs inside here. Now the air is rushing in, you might be able to hear it, and the scales now say about 2.5 grams. So there's 2.5 grams of air inside this flask. Well, okay, let's see how much 2.5 grams weighs. I've got a little jelly baby here, let's just see how much he weighs. Well, the whole jelly baby, there he is, he weighs about just over 5. Well, let's just rip off his head, perhaps. There we are. Oh, his legs are about 3 grams. So it's about a headless jelly baby. Okay. Now that doesn't sound very much, but just think how much air we have in the lecture theatre here. If we put all of this and we managed to weigh all of the air here, that would come up to about the same as a small elephant just in here, just the air pushing down. Well, let's see what else we can do with the air. I have a couple of balloons here, small little balloons. They're about the size of my fist, very tiny small balloons. I'm going to put them in here. Okay. Now at the moment, when I pick up a balloon, if I just get another one, the balloon isn't blowing up, it's not getting smaller, it's just staying that size. And this is because the balloon is of course full of air, and that's pushing on the walls of the balloon, but there's lots of air around us as well, pushing on the outside, and these two balance each other out, so it's not getting bigger or smaller. But if I take all of the air away from outside of the balloon, I have 2 balloons in here, you might be able to pick them up on the camera. And remember, these are about the size of my fist. And here we are, just taking the air out of this. And the balloons are actually getting bigger. So the balloons are getting bigger and bigger and bigger. And this is because, well, we're removing the air from outside, so there's nothing pushing against the balloons now, only the air inside. And that's pushing against the walls, making them get bigger and bigger and bigger. Still getting bigger. Oh! And now they've burst. And that was because there was nothing pushing against them. Okay, and so it's just the air pushing against the balloons from inside. Right. Now, I have one more flask over here. We've taken the air out of the flask, so there's nothing in here. But there's a tube running up the centre, and the tube goes into this large beaker of water here. Now when I open the tap, see the water being pushed up into the empty flask here. So this is the atmosphere, the air pushing down on here that's forcing the water up into the empty flask. Okay. Well, I have one more demonstration to show how forceful the air is pushing down on us. We're completely unaware of this, but it's actually the equivalent to 3 people sitting on my shoulders, pushing down on me. But of course, I'm used to this, so we don't notice it at all. But one more demonstration to show you, and for this I need a volunteer. I need someone to volunteer. I need somebody to volunteer their parents, please. Okay, oh, even more hands going down, and some hands going down. Oh, see, yeah, people just shaking their heads there. Says, oh, who are you volunteering? You got to, oh, okay, well, I'd like to come forward then, please, yes. And we need somebody else. Who are you volunteering? Oh, yes, there we go. If you could come forward as well then, please. Yes, you were very, very well volunteered there. Right, now, all you have to do is pull these 2 hemispheres apart. Now, they're made of metal, very solid, okay? And at the moment, we've got air inside here when I put them together, and air outside. But I'm going to take the air away from inside using the vacuum pump. So here we are, attaching the pump, taking the air out of here. So now there's no air inside, but there's still air pushing around, pushing these 2 together. Okay, so let's switch the pump off. Okay, and if you 2 would like to come one each side, one there, one this side, and see if you can pull those apart, please. Go on, try hard, really hard. Okay, I think that's fairly convincing. Yeah, thank you very much. Well done. Now, you shouldn't feel too disappointed that you were unable to do that. Here we have a team of 16 horses that were unable to pull these apart. Remember, this is the air that's pushing them together. It really can't remove them until I just let the air back in. Then it come apart easily. Okay. Right, so have one more demonstration here to show the effects of the air. And again, I've evacuated this flask, so there's nothing in here, apart from a coating of phosphorus. Now, phosphorus is very, very reactive, and when it comes into contact with the air, you may be able to see some light coming out. So I'm just going to open the tap here and let the air in, and you may see a flash of light. Very good. Okay. Thank you. So as the air came into the flask, it reacted with the phosphorus. Now, it's actually just one part of the air that was reacting there, and this part was discovered by this man here, Joseph Priestley, around the late 1700s. Well, he wrote a book about this. He wrote a book called Experiments and Observations on Different Kinds of Air. Well, now we probably wouldn't say different kinds of air. We would say experiments and observations on different gases. And this is one of the gases. The gas that he discovered here is the first one we're going to be looking at, and that's oxygen. So oxygen just makes up 20% of the air, and yet it's the most important gas for us. It's the gas that we breathe to give us our energy. Well, where does oxygen come from, the oxygen in the air? How do we get it? It comes from plants. And over here, we have some plants. We're having light shining on them, but unfortunately, I think we cooked them a little bit too much the other day, and they would normally be bubbling away, giving out oxygen gas, but I think we've, yes, killed them. Never mind. So usually, oxygen from the air comes from the plants, okay? Sometimes, though, we need an emergency supply of oxygen. Like that. Yes. So, in an airplane, if there was an emergency, these little masks would drop down and would be able to breathe in the oxygen. But this oxygen, it doesn't come from a canister of compressed oxygen. This oxygen is made chemically. Okay? Here's the apparatus that's used to make this. We see the masks here with a little bag, and here's the generator. It's a chemical generator. I have one here that's already gone off, and there's a compound in this called sodium chlorate. And in this, we have a chlorine atom combined with some oxygen, but when it's heated up, that oxygen is released, and we can use this to breathe in. Now here we have a chemical reaction to show this reaction. We have sodium chlorate, and as we heat this up, it forms sodium chloride, which is very different. So this has now lost the oxygen. Sodium chloride is, well, does anyone know what sodium chloride is? What's that? Yes? It's salt. Very good. Yes, this is actually the sort of thing that you'd put on your fish and chips. Just normal salt. Sodium chlorate is very different. This has oxygen built into it. You heat it up, it forms sodium chloride and releases the oxygen. Well, we can show this now. Have a very similar reaction. This is not sodium chlorate, but potassium chlorate. And Chris here has been heating up some potassium chlorate, releasing some of the oxygen. And I can show this with a wooden splint here. What I'm going to do is blow out the splint. So now it's not alight, it's just glowing. But if I put this into the tube, the oxygen that's being given off here relights the splint. So now it's out, and now it's lit again. And that's a reaction from the oxygen that's coming out as the potassium chlorate decomposes. Well, I can show another reaction with this. This time I'm going to react the oxygen in the potassium chlorate with another jelly baby. Right. So, here goes, go. God. Oh. Well, that was really rather violent. And that was all the sugar reacting with the oxygen from the potassium chlorate. And it's still going. Poor little jelly baby. There's not much left of him now. Well, we'll just leave that one going. So we've seen how the oxygen comes from plants most of the time, from photosynthesis. That's where the oxygen in the air comes from. We've seen that we can chemically generate this by heating up something like the potassium chlorate here. It's still going. It'll finish in a moment. There we are. It's just about to finish. Now, what if we wanted lots and lots of oxygen? If we didn't want all the rest of the chemical in there, if we didn't want the sodium chloride left over and so on, if we just wanted some pure oxygen, how would we get this on a large scale? Well, we could get this again from the air around us. If we cool down the air, if we cool it down to very, very low temperatures, we actually end up with, well, liquid air. And I have some liquid air here. And if I just pour this onto the bench here, okay, this is liquid air, very, very cold. Okay, but so cooling down the air, I get a mixture of liquid nitrogen and liquid oxygen, and I can separate those two out, and then I get some pure oxygen and pure nitrogen. Now, I have two test tubes. Here's one of them, okay, with a balloon on top. Filled up the balloon, so just with normal air, okay, and here's the test tube on the bottom. And I've put one of these, exactly the same as this one, into this cold flask here. And we can actually see the liquid air in here. So in the bottom of the tube, there's some liquid air, and it was just the same as this balloon, but cooling it down turns the gas, the gaseous air, into liquid air. And actually the balloon, look at it if you look closely, it's beginning to blow itself up. Okay? And this is as the liquid air turns back to the gas air. What I'm going to do, I'm going to swap these two over, put that one there, so that one will continue to blow itself up as the liquid turns back to the gas. And I'm going to put this one into the cold flask here. And so this one, the balloon, will gradually shrink down as the air condenses into the liquid. So keep an eye on those, and they'll change during the lecture. Well, we can use this liquid oxygen, once we've made this and separated it from the liquid nitrogen, we can use this as a very, very concentrated supply of oxygen. Now, why do we need oxygen? We need oxygen to give us our energy, the energy from the food that we eat. So I'm going to demonstrate this now. I have some food, some hobnobs. Okay, so let's take a hobnob out. And I'm going to put it into some liquid oxygen. Okay, so here's some oxygen. Now remember, the oxygen itself doesn't burn at all, but it enables things to burn in it. So adding some oxygen to my biscuit, make sure it's nice and soaked with oxygen. Get my biscuit out if I can. This is always the tricky bit. There we are. That's the biscuit out. Add a little bit more oxygen just to be on the safe side. Got to be safe. Yes. Right, and then apply a light, and you may be able to detect the energy coming out of this. Okay, now watch carefully. Okay, so I hope you noticed there the energy being released from the hobnob as it combined with the oxygen. Let's just get rid of that. Let's try some other food. Have here some Rice Krispies. Now on the side of the packet here, it says that 100 grams of Rice Krispies provides, it says energy, 1,600 kilojoules of energy. So that's an awful lot of energy in 100 grams of Rice Krispies, or 380 calories. Well, let's see if we can release that energy then by combining the Rice Krispies here with some oxygen. Okay, so there's the Rice Krispies. Add some liquid oxygen. There we are. And now we'll apply a light. Wow. Very good. So you can see all the energy being released there from the food, and this is very, very important. This is what gives us our energy. Okay, we eat our food, and it's, well, not quite so vigorous as that. It's a more controlled reaction, but nonetheless, it's the same sort of thing. This is how we get our energy from our food, the reaction with the oxygen. Now, the Rice Krispies and the biscuits that we saw there contain a lot of carbohydrates, and they contain fats. Well, these contain carbon combined with hydrogen and oxygen, and it's these that are reacting with the oxygen that we added there. And the carbon forms carbon dioxide. The hydrogen forms, well, hydrogen oxide or water. Well, we're going to look at this now. We're going to look at the properties of these other gases. Now, we can see the same sort of reaction. This is converting our food with oxygen into carbon dioxide, and I need a helper, and I need an adult helper, I'm afraid, and we have one just at the back there who's specially trained for this experiment. So Chris, if you can come forward, please. Now Chris is going to wear this rather scary looking apparatus here. So if you'd like to put this on, please. Okay. Now all Chris needs to do is just breathe. So if you breathe, now he's breathing out, so if you breathe in, now as he breathes in, okay, the air is coming through this tube, bubbling through the solution here, and as he breathes out, it comes out of this one. Okay, so in this one, out that one. Now you just keep breathing there, and we'll be showing you what's going on. I'm coming back round here. Now what Chris is doing there, he's converting his food with the oxygen into carbon dioxide. Now I thought we'd make a little bit of carbon dioxide over here. So I have a cylinder of oxygen, 2 cylinders of oxygen. So this is pure oxygen gas. And I'm going to make some carbon dioxide by heating up some carbon and allowing this to react with the oxygen in the gas jar. So heating up the carbon here. Need to get it nice and hot. So keep breathing, Chris, don't forget. Okay, heating up the carbon, and I'm going to pop this into the gas jar, and you can see it's reacting. It's glowing very, very brightly, and this is the carbon reacting with the oxygen in the flask here to form carbon dioxide. Now, we need to heat it up to get the two to react. If I just put in some carbon without heating it, well, nothing really happens at all. But how do we know if something has reacted, apart from the fact that we can see it glowing here? How do we know we've formed some carbon dioxide? Well, this is the solution that Chris is bubbling through at the moment. This is called lime water, or, well, the technical term for this would be calcium hydroxide solution. I'm going to add some of this to the gas jars here. So first of all, to the one with the that we heated up, like so, and then add some to the one that we haven't heated. And now I'm going to give them a little bit of a shake. And one of these, this one that we reacted, you can see is going slightly cloudy. This one isn't going cloudy, and the cloudiness that we see here is due to the formation of calcium carbonate. Well, we can show this, what's going on here, with the slides. So we have carbon that's been heated up with the oxygen to form carbon dioxide, and then that's combining with the calcium hydroxide, the lime water, to form calcium carbonate. The calcium carbonate, well, it's actually chalk, and this doesn't dissolve in water, and this chalk is precipitating out, and that's what makes the solution look cloudy. So if we come back to Chris now, you can very clearly see that the in one that's just had air going through this, but there's not very much carbon dioxide in the air. You can carry on breathing a bit more, that's it. Right, so the in one isn't very cloudy, but the out one has changed. We can see that this is quite cloudy now because of the carbon dioxide that Chris has made in his body by reacting his food with the oxygen. Thank you very much, Chris. Well done. Now, before I go on to show you some of the properties of carbon dioxide, I also want to heat up a little bit more carbon. So we have some carbon burning here. Thank you. And I'm going to add some of this. Is this any burning bits? Just that little bit. Okay. I've got some burning carbon here, some more charcoal. So this is also going to react with some air, but I'm going to put the lid on this container. And there'll be a slight difference. We'll come back to this one later. But again, it's just allowing the carbon to combine with some of the oxygen from the air. But we'll come back to that in a bit. We might need to, we might detect when something happens with that. Anyway, back to our carbon dioxide. I want to look at the chemical properties of carbon dioxide. And one of the properties is that it's heavier than air. Now, I've got a bucket full of carbon dioxide here. I'm just going to pick up this bucket, being very careful not to spill any, and I'm going to pour some of this into the bucket here. Now see if you can see what happens. Now I'm pouring it now. Can you see it coming out? No, it's invisible. But look what's happening to the bucket. Okay. So that's because the carbon dioxide is heavier than air, all right? So does anyone know the formula for normal oxygen that we breathe in? What's the formula, the chemical formula? A hand went up there. Yes, what's that? O2, that's right. And we see some O2s around here. And this, remember, means that there's two atoms of oxygen combined together to form the oxygen that we breathe in. Anyone know the formula for carbon dioxide then? Down here, yes? CO2, very good. Exactly. So oxygen was O2, carbon dioxide was CO2, so we've added an extra atom of carbon to this, and this makes it way heavier than normal O2, because we've got another atom in there, another carbon. This is why it's heavier, this is why the balance went down. Okay, well, we can show this with a balloon as well. So I have a tank here. I'm going to put some carbon dioxide into the bottom of the tank. Just going to sprinkle a little bit of this in. So this is going to make some carbon dioxide gas to go into the tank. And now I'm going to add two balloons. The balloons are just filled up with normal air. But look, they don't go all the way down to the bottom. They're floating in there on top of the carbon dioxide. Okay? And this is because the carbon dioxide is heavier than air. Now we can also show this with some candles. Okay, Mark's just lit the candles, and they're all different sizes. And I'm going to add some carbon dioxide to the bottom of the tank. Now watch the little candle over on that side. Oh, it's gone out. Okay, so the carbon dioxide is heavier than the air, and it's gradually filling up inside the tank, and now that one's gone out. When the level gets to the top of the candles go out. So this shows two properties. Oh, something's going off. What is it? It's my alarm here. Remember this one? Okay. What did I do here? I put some burning carbon into the tank, but I put the lid on, and now this alarm is going mad. Okay, I think I'll give that to Mark to take it away. So, carbon was burning, and we've seen carbon burning, and it forms carbon dioxide. But it can only form carbon dioxide if there's lots of oxygen to get there. Remember, carbon dioxide has the formula CO2, So we need lots of oxygen to combine with it. Carbon dioxide is safe for us to breathe in. We saw Chris breathing out some carbon dioxide. But in this tank here, when I put the carbon into here, this combined with the oxygen, but I put the lid on the top, and there wasn't enough oxygen to form carbon dioxide, and instead it was forming a very poisonous gas called carbon monoxide. And this only has one oxygen atom in each molecule. So the formula for carbon monoxide is CO, not CO2. And this is actually really poisonous. And this is why we have the little alarm here to detect it. This can actually poison us because it locks onto our blood, onto the hemoglobin that would normally help transport the oxygen that we need around our bodies, and it blocks the oxygen getting to us, and so can actually kill us if we breathe in too much carbon monoxide. And this is why it's always a very good idea, if you have a gas fire or a coal fire at home, to have one of these little alarms there to detect if the fuel isn't burning properly, then there can be a problem because we're making the poisonous CO. So it's a very good idea to have one of these detectors. Anyway, let's go back to our candles. I'll just add a little bit more carbon dioxide to this, just see if we can get some more candles going. Okay, hopefully those will disappear during the course of the lecture. But this shows two properties of carbon dioxide. One is that the carbon dioxide is heavier than air, but the other one is that it can also extinguish fire. It doesn't allow fire to burn in it, it puts it out. Okay? Well, let's see if we can show that on a slightly larger scale. Okay, I'm going to start a fire over here. I'll just remove these, put them out of the way. If we just move the Bunsen burner a bit. I've got some flammable liquid here. I'll just pour this on. Thank you. And start a fire. But here I have my carbon dioxide fire extinguisher. And it's put it out. So on the fire extinguisher, it says CO2. This is a carbon dioxide fire extinguisher, and we can see that it puts out the fire very nicely. I'll just set it off again. You ready? Okay. And did you notice when it comes out, sometimes you see some like snow falling out? Okay. Well, what this is actually a solid form of carbon dioxide. Now, carbon dioxide is really unusual because, well, when you cool down most gases, they turn into liquid. We saw that with the air. It forms liquid air, okay? But if we cool down carbon dioxide, it actually goes straight from the gas form to the solid form. And this is what I have over here. This is actually solid form of carbon dioxide. If I just sprinkle some of this on here, you'll see solid carbon dioxide. I better get rid of that because I don't want people touching it. It's very cold. But as this melts, it isn't going to form a liquid. It doesn't form a liquid and get messy everywhere. It actually goes straight from the solid form into a gas. Okay? And this is what you need if you want to be a real mad scientist. You have to add some carbon dioxide, some solid carbon dioxide, also called dry ice, because it doesn't melt and get messy. It just goes straight from the very cold solid form to the gas. But if I put this in some warm water, well, just normal water, there we are, mad scientist. This is as the solid carbon dioxide turns into the gas. Okay. So every mad scientist needs one of these. Every mad scientist also needs one of these as well, but we'll come back to that one. Okay. Now, so carbon dioxide, very unusual then because it goes straight from the solid to the gas. We can, if we're careful, still make some liquid carbon dioxide, and this is what I'm going to try and do now. I'm going to put some of the solid carbon dioxide into this very, very thick-walled test tube. There we are. So here I have some solid carbon dioxide in the test tube. I'm going to put the lid on this and do it up. And put this into some water here, just so it doesn't frost over. Now, what's going on here? The solid carbon dioxide is turning straight into a gas, and you can actually see the pressure building up inside this test tube. There's nowhere for the gas to come out. So the gas takes up much more space than the solid, and as the solid turns into the gas, nowhere to go, the pressure is building up, building up, building up. Well, this would be very dangerous, but there is a valve to let this out later. But look what's happening down the bottom here. As the pressure builds up, and it's just beginning to build up a little bit more, look what's happening to the solid carbon dioxide. It's melting. So we can get, there we are, liquid carbon dioxide. It's now forming liquid carbon dioxide, and there it is in the bottom of the test tube. Okay. It's melted to give me some liquid in there. There we are. Now if I release the pressure very, very quickly, okay, watch what happens. It's gone back to the solid as the pressure is released because it's still very, very cold. Now I'll close it off again, and then that will help it melt again as the pressure builds up, and the whole thing will do it again. This liquid carbon dioxide is actually really useful because we can use it to dissolve things that wouldn't normally dissolve in water. So for instance, if I wanted to extract the caffeine out of this coffee but leave all the nice taste of the coffee there, well, we can use carbon dioxide, liquid carbon dioxide, to dissolve the caffeine. And this was decaffeinated using this. This is a good way to do it because we don't need any poisonous solvents to dissolve the caffeine. Okay? We know that carbon dioxide isn't poisonous because we know that we breathe it out all the time. Okay, carbon dioxide then. So this is very much in the news as the greenhouse effect. You may have heard of the greenhouse effect, okay, and this is a problem. Every time we burn some petrol or burn some coal, we're producing carbon dioxide gas, and this is helping to warm up the planet. Remember, there isn't very much carbon dioxide in the atmosphere. It's only this small proportion here. But even over the last 50 years, the amount of carbon dioxide in the atmosphere has changed by about 20%, which is a huge change for something as important as our atmosphere surrounding the planet. Now, what effect has this had? This has helped the atmosphere warm up. Now, I should be able to demonstrate this over here. Two flasks here. One of these, the red one, we've added some carbon dioxide to. The blue one is just air. And we're recording the temperature inside here. You can see it's gradually changing here as I speak. They're getting new data points. But notice that the red one is heating up faster than the blue one. And this is because the carbon dioxide is absorbing some of this energy. But let's see what this greenhouse effect is all about. I mean, it's very, very important, and people keep going on about it. I'd like to try and demonstrate what it's about. And Chris, would you like to come to the front? Chris is going to be the Earth. Now, during the day, the sun is shining on the Earth, giving the Earth lots of energy, which is what allows us to live. Here is lots of energy. Well, these are photons of light. They're little bits of light energy. So here's a whole load of light energy given out during the day by the sun. Now, at night time, the Earth just gives out this energy. So that's what's going on here. Now, if I'm a molecule of oxygen or nitrogen, I don't absorb the energy. It just goes straight past. But if I'm carbon dioxide, I can capture this energy, and then I can give it out as well. And I might give it out that way, okay, like that. Or I can capture this energy, and I might just give it back that way again, back to the Earth. So let's just see that again. So the carbon dioxide captures the energy, gives it out maybe that way or maybe that way, back to the Earth. And so the Earth gets all this energy back again, and that helps to warm it up. But in order to capture that energy, we must have two atoms, two different atoms together. If we have two nitrogen atoms together, as in N2, that doesn't absorb. If I have two oxygen atoms together, that doesn't absorb. But when I have carbon with oxygen, carbon dioxide, that is a greenhouse gas. Okay, but even hydrogen with oxygen, water is a greenhouse gas. So many things are, but the normal air, nitrogen and oxygen alone are not greenhouse gases. So this is why it's very important when we burn gases, well, we're very conscious of the amount of carbon dioxide we give out because it can affect our atmosphere. Well, if we have a fuel without any carbon in, we're not going to form any carbon dioxide. And here we have a fuel without any carbon in. This is hydrogen. I have this right at the back, I think. And I'll need my stick, please. And I need my big stick for this one. Thank you very much. Okay, now you will actually experience this, okay? Right, you'll feel a bit of a force. I'm the closest person, okay? Right, are you ready? 3, 2, 1. Oh. Whoa. Good. So actually, what you just saw there was an environmentally friendly explosion, okay? Because no carbon dioxide was formed, so it wasn't polluting our atmosphere. All that was formed there was actually the hydrogen combining with oxygen to give water. And we can see this. Hydrogen combines with the oxygen gas, and this forms, well, a technical person might call this hydrogen oxide, but every normal person would just say it's water. So the hydrogen combines with the oxygen to form water. And as you all know, the formula for water is H2O, meaning that 2 parts of hydrogen combine with 1 part of oxygen. Well, you saw all the energy being liberated there as the hydrogen combined with the oxygen. And I wondered, well, what would it be like to have a really big balloon and to strike a match inside that balloon? Can you imagine that? Well, I thought we'd demonstrate this. For here we have a bag with some hydrogen. I'm just looking for, here we are, my face shield here. Okay, and we also have our helpers standing by with fire extinguishers and a safety blanket. Now, I'm going to put my special gloves on and I'm going to get inside this bag full of hydrogen. And I've put some matches inside here. Okay, and I'm going to strike a match. All right. Now watch very carefully as I strike the match. Ha-ha. I hope you can all see that the match does actually strike and it does light and there is a flame inside here. I'll do it again. Okay, once more. But the hydrogen doesn't explode, thank goodness, because I really don't want it to. Whew. Now the question is, why doesn't the hydrogen explode? Why doesn't it explode? Anyone know? Because there's no oxygen in there, that's right. Remember, hydrogen needs oxygen in order to explode, to react. Okay? The match has oxygen built into it. It actually is the same sort of chlorate that we saw with the jelly baby. So that has a source of oxygen built into it. So when I strike the match, that can light because it has some oxygen built into it, but there's no oxygen in there to combine with the hydrogen. So there's no reaction at all. Phew, that always makes me nervous, that one. Right. Now, we can use hydrogen for our transportation and so on, and I need a volunteer to come down and help with this, please. Yeah, right on the end there, why not? Yes, you'd like to come forward, please? Right. Okay, sorry, what's your name then, please? Sophia. Sophia. Okay, right. Now, Sophia is going to launch a rocket here. We have a rocket at the back filled with hydrogen and oxygen, and Mark's going to give you your safety equipment. I'll just explain what's going on here. So the rocket here is filled up with hydrogen and oxygen. And in a moment, we're going to put an electrical spark across there, which should, I hope, send our rocket across. So we'll have a countdown from 3. Okay, 3, 2, 1. Oh, well done, very good. Thank you very much. Thank you. Now, obviously, that was rather a small rocket. Here's a larger rocket. This is the space shuttle. But actually, the orange tank in the middle there is filled up with, well, a very concentrated supply of hydrogen and oxygen. It's liquid hydrogen and liquid oxygen. And this, when they react together, gives a lot of energy and helps thrust the rocket up. The white rockets either side, well, those don't contain hydrogen and oxygen. We'll come back to those ones. But the blue flame that we see here, not the yellow flame, but the blue flame is the hydrogen and oxygen combining, helping push the space shuttle into space. Well, closer to home, here we have a car that's powered by hydrogen. And so this doesn't emit any carbon dioxide. So this isn't bad for the environment at all. And you may have seen these motorbikes recently on the news. This is Intelligent Energy's ENV fuel cell motorbike. The ENV there stands for Emissions Neutral Vehicle. So this is the vehicle of the future, non-polluting, just uses hydrogen combining with oxygen to form water. Now, you may have noticed in each of the reactions where we've caused hydrogen to combine with oxygen, I've had to supply some energy. either a lighted match or this spark that we saw there. Well, actually it is possible to start this reaction without adding any extra energy. And this is what I'm going to do now. Now Mark here is just going to fill up a bottle with some hydrogen. And I'm going to add some very, very finely divided metal called palladium metal. This is a rather rare metal, quite expensive to buy. I'm going to put some on a little cotton bud here. Okay, so this is now full of hydrogen. Hydrogen's lighter than air, so it's trapped in here. I'm going to turn it upside down. Oh, there we are. So the catalyst, the metal there acted as a catalyst, allowing this reaction to take place. Now, catalysts are very, very important. You may have a catalyst in your car here. So here we have a catalytic converter that we can see on the slide. And this has some of the metal palladium and platinum in it. I'm going to heat up the surface of this using a flame of hydrogen. Okay, so now it's nice and warm. This will help the reaction start. There's no flame now, no flame anywhere. But now watch what happens when I just put the hydrogen onto the catalyst. First of all, you should begin to see it glowing. Oh, maybe not. Oh, they are glowing red hot, and then it can actually light the flame here. Okay, so this is the metal here is helping to catalyze this reaction, to start the reaction. So there's no flame at the moment. There we are. Very good. Thank you. Thank you. Just back in. So the catalyst here in the car, well, it's not normally used for the reaction between hydrogen and oxygen, okay, because most cars don't have hydrogen in them. What it actually does is help convert, remember the poisonous carbon monoxide? Well, this will ensure that the car doesn't give out any carbon monoxide. Instead, it's all converted to the safe carbon dioxide that it's okay for us to breathe. It also helps convert poisonous oxides of nitrogen, and we'll come back to we'll see some oxides of nitrogen later. It helps convert those back to nitrogen gas, which again is perfectly safe to breathe. So that's the role of the catalytic converter there. It helps convert these poisonous gases into ones that are safe to breathe. Okay, now, talking about the space shuttle, remember I said that these white rockets either side here, these are solid rocket boosters. And these don't contain hydrogen and oxygen. These contain, well, actually, as the source of oxygen, they also contain the chlorate that we saw earlier. Okay, so there's a source of chlorate in there. And the chlorate, remember, gives out some oxygen. And this is actually giving it to aluminium. There's a very violent reaction between the oxygen from the chlorate and aluminium here, forming aluminium oxide. But this provides the thrust for the rocket as well. Now, I thought when I was trying some of these rockets at a friend's house a few days ago, this is one of these rockets. It's sort of like a firework rocket, and inside this we'd put a little tiny firework rocket, put this in and set it off, and it would go up about 1,000 feet. Now I wondered when we were doing this how much gas comes out of this. So this little canister here generates chemically formed some gases that get shot out the bottom very, very fast, shooting the rocket up. Well, I thought it'd be interesting to see how much gas comes out, and so we've got one inside this very, very strong steel container here. Okay, so there's the rocket in the top, and the tube comes up into this tube here full of water, and when we set the rocket off, you should see the big air bubble coming up. So we can see how much gas then is needed to send this little rocket 1,000 feet into the air. So we have a countdown from 3, 3, 2, 1, and there we are. So this is the amount of air coming out of the rocket very, very quickly indeed, can shoot the rocket up into the air. Okay, now we're going to look now at the most abundant gas in the atmosphere, and this is the nitrogen. Remember, this makes up most of the air. It's the yellow colour from my coat. This makes up 80% of the air. Nitrogen. Nitrogen has very, very different properties from oxygen. So I have a candle burning here. I'm going to add some concentrated nitrogen, liquid nitrogen to this. Just gently pour it in, and you see it's already put the flame out here. So oxygen enables things to burn. Nitrogen stops things from burning. Nitrogen does not support combustion. Well, this is actually a really good thing. And we can demonstrate this as I go behind here. Suppose then for a moment, suppose that the air that we breathe in was just all pure oxygen. No nitrogen, just oxygen. Well, I'm going to make the air inside here pure oxygen. Going to add my concentrated oxygen, my liquid oxygen. There's just some sand in the bottom here. Okay, so now there's lots and lots of oxygen in there. And imagine you were in here, or you visited a planet where the only gas in the atmosphere was oxygen. So here we have a little man. Well, this isn't obviously a real man, but it's made of meat. It's a little sausage man. Okay, now supposing then on your foreign planet where the atmosphere was just oxygen, suppose that you accidentally leant onto the hot plate of a cooker, for instance. Well, let's see what happens. We just added a hot wire here, and his leg seems to have caught fire. Okay, and he seems to be burning. Well, this is like spontaneous human combustion here. Okay, just accidentally leant on a bit of a fire, and he's gone up. Okay, and he seems to be going up rather vigorously. I don't know if any more is going to catch fire. Maybe we can help a bit more catch fire if I add a bit more light. I don't know if this is a bit cruel, but see if we can get this arm to go up as well. Oh, there we are. Yeah, I think we maybe add a bit more liquid oxygen just to be on the safe side. Oh, there we are. Remember, the oxygen doesn't burn, so it's not like pouring petrol on a fire, which would be a really silly thing to do. Oxygen enables things to burn, and my poor little sausage man is definitely burning very vigorously now. So, the point is, it would not be a good thing to go to a planet where the only gas is oxygen, because everything is going to be much more flammable. In fact, it's been calculated that if our atmosphere changed by about the amount of oxygen by about 10%, so if there was 30% oxygen, every time there was a forest fire, we wouldn't be able to put it out, and this would use up all the oxygen and cause for more carbon dioxide, and actually life probably wouldn't be able to exist if there was initially more oxygen. Okay, so it's a good thing that there's a lot of nitrogen that stops things from burning. I think I need to try and put him out before we all have lots of sausage smells burning and make everyone hungry. I'll put him out with some tomato ketchup. Okay. There. Perfectly safe. Okay, so nitrogen. Nitrogen is very unreactive, okay? And this is because we have the two atoms of nitrogen held together, not with one or two bonds, but with three bonds. So this is a very, very stable molecule. It doesn't really want to do anything. It doesn't let things burn in it. It's a very stable molecule. Now, I've got a compound with some nitrogen in it. This is called nitrogen triiodide. So here we have nitrogen combined with iodine. And again, the nitrogen doesn't really like to be combined with the iodine. There's very, very weak bonds between these two. The nitrogen really wants to bind to itself instead, forming the very, very strong nitrogen-nitrogen bonds. Now, this compound is so unstable that if you just touch it, it may well explode, reforming the nitrogen gas. So I'm just going to throw a photon at my nitrogen triiodide, which is in the corner over here. So I need to put my ear defenders on, and I'm afraid you'll have to put your fingers in your ears for this one. Now, I hope I can actually get a photon to land on this. Let's see. There we are. So the reaction that was taking place there was this very reactive nitrogen triiodide that isn't very stable. Instead, it reforms nitrogen combining with itself, nitrogen gas, N2, and also the iodine. So the purple cloud that we see there is actually the iodine. And this is the sort of thing that you might put on a cut if you have a cut on your finger. Now, this reaction, or one similar to it, is responsible for saving thousands of lives. And Chris here is going to demonstrate this. Okay, so Chris has his special car here. Okay, I hope you like his special car. He spent ages making it. And it's used his partner's furry dice here. I hope she didn't mind. Anyway, so she didn't have much choice. Anyway, so now on the car, somewhere in here we have the steering wheel, and in the steering wheel there is an airbag. Now this airbag contains a compound called sodium azide. This is sodium combined with nitrogen. But again, this isn't a very stable compound. Really, the nitrogen wants to combine with itself instead to form the very, very stable nitrogen gas. So we're going to count down in a moment and see if we can set this airbag off with an electrical current. Now, it might be quite loud. Some of you might want to put your fingers in your ears if you don't like loud bangs. It's not too bad. Okay, so we'll have a countdown from 3. Need to watch very carefully, because if you blink, you'll miss it. 3, 2, 1. There, very good. Okay, and Chris is going to wheel that away. So the airbag there contains sodium combined to nitrogen, and with an electrical current, it releases this nitrogen, inflates the bag, and actually, if you hit the bag, if you were unlucky enough to be in an accident, as you hit the bag is actually going down again. There are big holes in the back of the bag, and the air is coming out, so you hit it as it goes down, not as it's blowing up, because that's coming out rather forcefully. In order to inflate it so quickly, we need to have an explosion there to generate the nitrogen gas. Okay, well, nitrogen, very, very unreactive. Okay, this is because of the nitrogen-nitrogen triple bond. We can get the nitrogen to react with, say, the oxygen in the air, but we need to supply a lot of energy. And this is what this apparatus can do here. So in a thunderstorm, all the energy from the lightning can actually cause the oxygen and nitrogen to combine together. And this is what we have here. This is called a Jacob's ladder. Now, across the two metal rods here, at around 7,500 volts of energy. And this can enable the nitrogen to combine with the oxygen. Well, how would we know, though, if the nitrogen is combined with the oxygen? Well, we should be able to see a change in the colour. First of all, the nitrogen combines with the oxygen to form a gas called nitrogen monoxide. But this is colourless. The gas jar here, I've put a white card in this to help us see it, but the gas jar contains nitrogen monoxide. Now, this gas jar just contains air. But when the nitrogen monoxide reacts with more oxygen, so nitrogen monoxide plus more oxygen, forms another gas called nitrogen dioxide, and this is actually a brown colour. As soon as the two gases mix, the brown colour is formed due to the nitrogen dioxide. So if we keep an eye on the air inside this glass tube here, this will gradually go brown as the energy from across these two electrodes helps the nitrogen combine with the oxygen. But in order to break up our nitrogen molecule, we need a lot of energy. Well, this apparatus here, and remember this is what I said every mad scientist needs, this is a special bit of apparatus to show this. This is my Tesla coil, and this can generate lots of energy. Right. Okay, turn it on. And if we have the lights down, So the purple colour was due to the nitrogen gas being excited by all that energy, and this can cause the nitrogen to combine with the oxygen, and we can certainly see that the air in here is now taken on a brown colour due to the formation of the nitrogen dioxide gas. Well, this can also generate the nitrogen dioxide gas, but you may be able to detect the odour of something else, and this is the same sort of smell that you might have noticed in a fairground on the Dodgem cars, or perhaps when you use an electric motor like a drill, and this is ozone. This is where oxygen, normal oxygen, O2 molecules, take some energy, in this case from the lightning here, and form O3 molecules, ozone. Okay, this is actually a very important gas. This surrounds the upper part of our atmosphere, and as very high energy particles of light come to the Earth, this reacts with the ozone or the oxygen here, and the air can absorb this and protects us from getting all this nasty energy from the sun. So it's very, very important, this ozone that's formed here, but ozone is a form of oxygen. Well, I can demonstrate here with the fish tank the formation of ozone, O3. What I'm going to do now is pass an electrical current through the air before it gets to the fish tank, and this is going to form some ozone. This ozonizer is used in fish tanks to help purify the water by getting rid of all the nasty things. Now, just as I've switched this on, it's beginning to form some ozone, and I've added a dye in here that reacts with the ozone so we can see it. So this shows that ozone O3 is very, very different from oxygen O2. I mean, the oxygen has been bubbling through here throughout the lecture and nothing changed colour, only when I add some electricity to the air beforehand, which generates some O3, some ozone, do we see the colour change. Okay, well that's just about the end of the lecture. Before we finish, I suppose I want to mention some of the gases that are in very, very small components. Well, one of them is argon. Okay, this is the 1% that we see here, the red colour of the pocket, and this is in the same family of gases as helium that we see, the light gas floating up with our balloons there, helium, neon, argon, krypton, xenon. We're going to show one property of helium. Well, the property is, of course, that it's lighter than air, and this is why we use it to fill our balloons. But why is it lighter? Each atom of helium is much, much lighter than oxygen. And remember, we saw the effects of the air pushing down on us. Well, if helium is used instead, it doesn't push down so much because it doesn't weigh so much. And this can actually affect my voice if I breathe in some helium, which is what I'm going to do in a moment. Well, as I'm speaking, my vocal cords are vibrating, but they're pushing back the air, which is what you're hearing. You're hearing the vibrations in the air. But if I breathe in some helium, because helium's so much lighter, it doesn't have to push so much, and actually my vocal cords vibrate much faster, and this makes my voice go up. So here we have some medical helium and oxygen mixed up in just the right proportions to allow me to breathe it safely. So I'm going to try breathing in this mixture of helium and oxygen.
So now if I speak, my voice has indeed gone up. Okay, I hope you appreciate this. Is my vocal cords vibrating faster. It's beginning to return back to normal now, thank goodness. But this demonstrates because helium is so light, my vocal cords vibrate much faster. Oh, right. Now that really is just about the end of the lecture there. But I think it's always very important to go out with a bit of a bang. Well, for those of you that came last year, you will remember the little bunny. Well, this time we have a little sheep. Okay. And so we're going to now convert this poor little sheep into some gas, I think. Okay, so here he is. Okay, I have the lights down. So now he's a solid, and let's make him a gas. All gone. Thank you very much. Thank you.